right, ladies and gentlemen, children of all ages. I don't think that we really need an introduction for Alex. Yes, the laughter in the audience tells me I'm right. But Alex is a distinguished professor of astronomy at Berkeley. He's one of the most heavily cited astronomers in the world. He won the Professor of the Year award 9 times, a record-breaking 9 times at Berkeley. What was the other education award that you?
It was the 2006 Carnegie Case National Professor.
The Carnegie Case Professor of the Year award. Yes. Among doctoral institutions. Okay, well,
there's several categories, you know.
Yes. And he has over 120 television appearances. So, like, I've heard many of you commenting, "Oh, I know who that person is. I've seen him on," and yes, he's on quite a few shows. And then he also has produced, 5 lecture series on astronomy, and I think he's got one here with a few for sale.
Should have brought more.
Yes.
Forgot.
All right. And then I was embarrassing him with this over dinner a little while ago to give you an idea of what kind of person he is. A number of years ago when he came out and was giving these talks, he gave me a copy of his business card, and on the back it says, "Keep spreading your passion for astronomy," and signed it.
Specifically to JD.
Yes, it's specifically in my name right there. Okay.
Look at the date.
And yes, June 24th, 2010.
June 24th, 2010.
So, thanks for that, and I will turn the time over to you.
Yeah, aloha, everyone. Yeah, all right. Great to be here. Yeah, it's been a while since I've given a talk on Maui, so this is a different venue, but anyway, I see some familiar faces and some unfamiliar faces. Always good to have new recruits to astronomy, so thank you for being here. I had a couple of nights on the Keck telescopes last week, right when that major storm that all of you know about was passing through. We had 70-mile-an-hour winds on Mauna Kea, never got close to opening. Second night, I think, snow started falling, but anyway, I have another night coming up in a few weeks, but of course, the time is very precious and hard to get, and you take what you can get. But I love the Hawaiian Islands, both for the people, the scenery, the ambiance, and of course, the astronomy here is just incredible. So. And it comes with the support of you, the people of the Hawaiian Islands. So thank you, and anything you can do to put in a good word for astronomy is always very much appreciated. But today I thought I'd tell you not about ground-based astronomy, like what is done up on Haleakala and Mauna Kea, but rather exciting results with NASA's James Webb Space Telescope, because it's been in the news a lot ever since being launched on Christmas Day 2021 aboard an Ariane 5 rocket. After many, many years of delays, but better late than never. And had they launched it 10 years earlier, as had been planned, it simply wouldn't have worked. So really tickled pink that it's up there right now. There are the inevitable comparisons with the Hubble Space Telescope, which has been serving us for 35 years now. The comparisons are often in the form of a cartoon like this. The new kid on the block, he thinks he's the center of the universe, says the Hubble Space Telescope. I hate him. Webb with a smiley face there. I'll try to explain how the Hubble is not irrelevant. I'm a Hubble hugger. I'm also a James Webb Space Telescope hugger. They're both still very, very good. Or, well, Hubble is still very good, and James Webb is the new kid on the block, but is also very good, but for a different purpose. So let's make some comparisons. First of all, the Webb has a much, much bigger primary mirror, 6.5 meters in diameter instead of 2.4 meters. Okay, and so you can think of a telescope as a gigantic pupil of the eye. You know, your eye dilates at night to let more light in. There's also a chemical change. Your receptors go from being the cones, which are sensitive to color, to rods, which are sensitive to black and white, but are more sensitive. Anyway, forget about all that. Your pupils dilate to allow more light to come in. And so the bigger the collecting area of a telescope mirror, the more light you get. The collecting area of the Webb is about 6 times greater than that of the Hubble, so it gathers light 6 times faster. In a given amount of time, it can see a star that's 6 times fainter, for example. So that's clearly one major difference. Another difference is that if you pass light, like sunlight, through a prism, you get visible light. And that's what we see, of course, optical or visible. And then there's the ultraviolet, which is what burns you. So, you know, the ozone in our atmosphere blocks most, but not all the ultraviolet. So wear your sunscreen 50 or whatever. I have no stock in sunscreen companies, but wear your sunscreen. So the UV is of interest for astronomers to study, and the Hubble studies visible light and the ultraviolet, so that's really great, okay? The Webb studies only the red tail end of visible light, and then what we call the infrared, longer wavelengths than red. And that's often called heat radiation because that's what you feel from hot coals, okay? Now the visible light you see, the orange and red, is just the short wavelength, sort of high energy tail end of the so-called spectrum, the distribution of light or electromagnetic radiation that coals emit. Most of the light is coming out at infrared wavelengths, and that's what you feel as warmth on your skin. So the infrared is often called heat radiation, and the Webb observes the infrared, mostly the infrared, only a little bit of the red there in orange, okay? That's very different from the Hubble. And so the Webb complements, does not replace or succeed the Hubble Space Telescope. I get really upset when in the media I see articles about how Webb, the successor of the Hubble, you know, blah, blah, blah. But often the reporters are just telling them, the public, what they hear from scientists. And so I've actually heard some of my colleagues refer to the Webb as the successor of the Hubble, and I get very annoyed at my colleagues because they should know better, okay? Right? And of course the media then gets it wrong if they're being told by some astronomers that this is the successor. No, they're complementary to one another, and I have programs still on the Hubble Space Telescope in its 35th year, and now in the third year, I guess, of the Webb. Okay, and then the third difference is that the Hubble is in what's called low Earth orbit. We've all been hearing a lot about low Earth orbit recently because of all the junk that's being placed up there. You don't want to launch junk up there, but the junk is defunct spacecraft and things like that. Elon Musk's thing, Starlink, right. You know, they're launching a bunch of things there to improve communication throughout the world. But there's also a lot of junk up there. And you know, if the things collide with one another, you have to worry about additional collisions. But anyway, low Earth orbit is getting pretty populated. We hope nothing hits the Hubble. It's about 340 miles up. That has its advantages and its disadvantages. The advantages are that shuttle astronauts, before the space shuttle program was discontinued, but still the Russia can get up there or whatever. But it could be serviced, you know, and every 4 or 5 years the Hubble was serviced. And so aging instruments were replaced with new detectors, and solar panels were replaced, and gyroscopes that help point the thing were replaced, and all kinds of things were replaced. And there was even the servicing mission because the mirror, though beautifully smooth, had the wrong global shape. So it's great to be in low Earth orbit from that perspective. But the problem for an infrared telescope like the Webb is that if it were in low Earth orbit, it would get way too much light and radiated heat from Earth, and that would swamp the signal from the faint objects that the Webb is trying to detect. So you want the telescope to be pretty far from Earth and its heat, its radiated heat, okay? So you can't place it in low Earth orbit. So it's placed at something called the second Lagrange point, which should have been called the second Eulerian point because a mathematician slash physicist named Euler first figured it out. In fact, he first figured out the first three, and then Lagrange figured out the more subtle L4 and L5, but somehow all five of them became known as Lagrange points. Anyway, here it is, 1.5 million kilometers, about 4 times the distance to the moon, away from Earth, okay? At a place that's semi-stable. That is, you put a satellite there and it pretty much stays there. It gradually wanders away, but if you have some little thrusters, you can nudge it back into place. And it orbits the sun in exactly 1 year. So it's collinear with Earth and the sun, and it just goes around and around, okay? So that's kind of cool. Now you might think, well, all right, it's pretty far from Earth, so Earth's radiated heat won't be terrible, but it's not much farther from the sun than Earth is. It's only 1% farther from the sun than Earth is, and so it gets a lot of sunlight, and it would heat up as a result of that sunlight left to its own devices. But it turns out there are these 5 thin sheets. They're almost like bed sheets, but they're not the material of bed sheets. I'll show you. They're polyimide, Kapton E variety. I'll show you that in the next slide. But these sheets are amazing because, everything okay with the zoom and all that? Yeah, okay, good. Because the hot side, that is the sun-facing side, is at 260 Fahrenheit, or 125 Celsius if you prefer. And the cold side is at minus 390 Fahrenheit. For a 650 Fahrenheit differential, as a result of these little bed sheets. So the telescope mirror and all the instruments back here and the secondary and all that, they're all cold and they don't emit much infrared. So that doesn't swamp the signal from the distant, faint sources that we're trying to study. So how do these things do this? Well, first of all, they're amazingly reflective, so most of the sunlight that hits them gets reflected away, but some passes through and then it bounces around because this second layer is very reflective and it eventually goes out the side. But some makes it through and it bounces around and most of it goes out the side. And so it does this, over 5 sheets, and by the time you get to this other side, you're at minus 390 degrees Fahrenheit. Absolutely astonishing. And these things are thin, 1/20th to 1/40th to 1/20th of a millimeter. Here it is, polyimide film, Kapton E variety, whatever. Pretty astonishing. Okay, well, these things are the size of football fields, and the mirror is 21 feet in diameter, so you can't fit all this thing in a rocket, right? There are none that are that wide. So it all had to be scrunched into a container the size of a school bus or something like that. And then on the way to the L2 point, it had to unfold, okay? And so here's an expensive NASA animation on how it all unfolded. And you can watch all the various things that had to happen. But there were 344 potential single point failures. By that I mean, if that one thing goes wrong, the whole mission goes kaput, okay? Forget it. Suppose each of them has a 99% chance of probability of working correctly. That sounds pretty good to me, 0.99. But these are all independent. So 0.99 to the 344th power, which is what you need to do, you have to multiply it by itself 344 times, is 3%. I gave this darn thing a 3% chance of working before it was launched. I was one of the pessimists. I was totally wrong. It's in fact working something like 25 or 30% better than the original NASA specifications. So hats off to the clever engineers who figured all this out. They had various things that would jiggle these bed sheets so that they would unroll properly. And you're seeing now the triptych, the mirror was like a triptych, and it had to unfold, and this whole secondary support structure had to come out. The first time you see this video, it's sort of mesmerizing. But it all worked, and a few months later, the thing was at the L2 point, and then they started adjusting the placement of the different mirrors because, when they unfolded them, they're not necessarily all looking at precisely the same point in the sky. So that's pretty cool that it all worked. Okay, so here's the sun-facing side. It's got solar receptors, it's solar panels, basically. That's how the thing is powered. It's also got a radio receiver and transmitter. It gets commands via radio signals from Earth, and it sends the data as bits of zeros and ones. Okay, and then here's the observing side with the telescope, okay? So then you might wonder, well, the solar panels need to get sunlight. So if the telescope, Earth, and the sun are exactly collinear, then what would the telescope see when looking back toward Earth? What would it see? An eclipsed sun, that's right. Almost totally eclipsed. Actually, the Earth would look a bit smaller than the sun, so it would be what's called an annular eclipse. And that would cut off too much of the power. Moreover, the sun, though primarily an optical and infrared emitter, it does emit some radio waves, and the sun is so big that the radio waves from the sun would dwarf whatever signals Earth astronomers are sending to the telescope. So you don't want these things to be exactly collinear. So what do? Well, it turns out we know the physics of this pretty well. Here's the L1 point over there. This is badly not to scale. L2 is not twice as far from the sun as Earth is. It's 1% farther. But anyway, here's L1. That's stable as well. And there have been satellites there before. In particular, the Solar and Heliospheric Observatory, SOHO. It monitors the sun 24/7, looks for solar flares and eruptions and stuff. We can tell the power companies when to shut down the grid so that the transformers don't get short-circuited. And in a very natural way that's really quite subtle, I'm not sure I understand the physics and math of this, but the natural trajectory at the L1 or L2 point is what's called these halo orbits. Things just go around in circles. This is a bit of a perspective plot, so it looks like an ellipse, but I think those are circles. And they just do that, and occasionally maybe the thing will start wandering away, but like I say, little thrusters will push it back into place. So there's this pattern at the L2 point as well, and so that's all they had to do. It's a roughly circular orbit around L2, so that Earth doesn't block the sun, you don't have an eclipse, solar panels will get the necessary sunlight, and you can get faint radio signals transmitted from Earth because the sun is not behind Earth directly. Okay, so once all the mirrors were aligned and stuff, because there are little 18 mirror segments, we saw this picture and everyone oohed and awed. And you should ooh and ah because already you're seeing galaxies here, giant collections of stars gravitationally bound together. But a lot of people ooh and ah because of this. You'll see a lot of these things in the pictures I'm about to show. Your reaction should be yuck, not ooh, because this is not what stars look like. This is what's called a diffraction pattern. It is something we can't avoid. It occurs when light interacts with obstacles, and in particular, when light interacts with the edges of these hexagonal segments, it makes 6 of those spikes, and when it interacts with these struts, it disperses light into those spikes as well. Now, 2 of the struts holding up the secondary mirror are aligned parallel to the sides of the hexagons, so they just add to the light. But the 3rd strut couldn't be aligned parallel. A triangle does differ from a hexagon, and so that's what produces that fainter strut out there. And we just have to remove this with software. So if you're studying this galaxy, you're hosed a little bit, but you measure the amount of light there, and you subtract it from this. And if your object is really faint, A better plan would be to wait a while, and then this whole pattern rotates, and so then that galaxy will be in the clear. But this is definitely a pain in the rear, okay? And so say yuck whenever you see the pictures, okay? All right. The other thing that you should keep in mind is that I'm going to be showing you visible light representations of light that is intrinsically infrared. Okay, you can't see it. You might feel it, but you can't see it. So the way this is done is that long infrared wavelengths will be assigned red, R, in the color palette, medium infrared wavelengths, G, green, and short infrared wavelengths, blue, B. Okay, so you get an RGB image that's representative of the infrared light that's actually being detected. But keep that in mind every time you see a Webb image in the news. They rarely tell you this, okay? But it's an optical or visible representation of intrinsically infrared light, okay? All right, well, let's get into some of the science. Why study the infrared? First of all, different wavelengths reveal different physical processes. And let me start by showing you an example of this. Here's the same object, a cluster of galaxies viewed at different wavelengths. So here's visible light, and there's a bunch of galaxies here. These are, again, gravitationally bound collections of millions, billions, in some cases trillions of stars. And there's a bunch of galaxies here gravitationally bound together. And you're basically seeing stars, okay? And this whole structure is about 1 million light years on the side. A light year is the distance light travels in a year, a very large distance, 6 million miles, 10 trillion kilometers. Don't try going, at 55 miles an hour, and certainly not at the speed along which I was going along the P.E. Highway today. I wouldn't call it a highway at 4 o'clock in the afternoon, at least not today. Anyway, okay, so that's visible light. But now let's look at X-rays. And this is a visible light representation, not of different wavelengths of X-rays, but white means brighter X-rays and blue means fainter X-rays. But anyway, what you see here is a whole bunch of diffuse gas that turns out to be hot, like 10 million degree gas, that's sort of more or less spread throughout the cluster, and you wouldn't have guessed that it's there unless you observed at X-ray wavelengths. So that's something new. And then here is a visible light representation of radio wavelengths. Again, in this case, it's not different wavelengths, but different brightnesses. The white is brighter, the blue is less bright. But here is the center, I think, of that galaxy there. But shooting out of it are these jets of particles. And it turns out these are very rapidly moving electrons zooming around in magnetic fields. Let's not get too much into the weeds. But again, this is an entirely different process than what we're seeing when we see starlight, okay? So radio, visible X-rays all tell us different things. It is reasonable to assume that the infrared will tell us something new as well, okay? All right, so I'm gonna sort of discuss 4 main science areas where the infrared is advantageous, but in conjunction with optical and UV, okay, I'm still a Hubble hugger. You can study the evolution of galaxies. So how did these structures of 100 billion stars form? How do they evolve with time? All right, those are interesting questions. We live in the Milky Way galaxy. It's not this one. If anyone has a picture of the Milky Way that looks like this, see me afterwards. I'd like to purchase usage rights from you. But we're like the mouse in the maze. It's hard for us to tell what the maze looks like, okay? But from outside it, you can tell. And this is a different galaxy, but it looks a lot like what we think our Milky Way looks like. And so it's of interest to know how these things formed and how they evolved with time. And although we personally can't go back in time, we can look to progressively greater distances. And because light doesn't travel infinitely fast, by looking progressively to greater distances, we're looking progressively farther into the past. And so if we make some assumptions about how galaxies, well, there are different types, so you have to worry about that a little bit. But in general, if you look at galaxies billions of light years away, you're seeing them as they were billions of years ago, and you can compare them with what they look like now, okay? So that's the idea. And if we want to see the formation of galaxies, we've got to look way far back, like nearly to the beginning of the universe, 13 billion years ago, let's say, out of 13.8. But the universe is expanding, and JD reminded me that I think my 2010 talk was about the expansion of the universe, but I try to choose something different each time, right? And the expansion of the universe stretches light into longer wavelengths. So if the stars in the galaxies long ago, far away, emitted ultraviolet and optical light, by the time that light reaches us, the expansion of space stretches it into infrared wavelengths. And so using the Hubble, you could not see the formation of the very first galaxies because the starlight that they emitted would have shifted to the infrared beyond the wavelengths that to which Hubble is sensitive. So we have to use infrared telescopes to study galaxy formation and early evolution. And here was the first photograph released by NASA on July 11th, actually 2022. And you might say, ooh, look at that wonderful thing. But really, you're supposed to say, yuck, thank you. You are very good students. You've already got at least a B+, okay? And so there's a whole bunch of, some astronomer might be interested in those stars. They might have an exoplanet orbiting them. But the point here is that this picture, which represents just a size in the sky equivalent to a grain of sand held at arm's length, okay? There are thousands of fuzzy blobs here. 1, 2, 3, 4, 5, 6. I could use up my remaining hour counting galaxies. That would be pretty boring for you, but it's a rather cushy job. They pay me to sit around and count galaxies, so I have to pinch myself. Anyway, there's a few thousand of them there in a grain of sand, and we've taken a number of such photographs now, and so we can estimate that within the realm of the Webb, there's something like 1 trillion galaxies, 1 million galaxies. And that's, broadly speaking, consistent with what we already knew from the Hubble, a few 100 billion. Okay, so that's not new, but it confirms it confirms and extends the number that Hubble had found. But they're just beautiful, and the point I first want to make is that some of these little blobs might be 8, 9, 10, 11, 12, even 13 billion light years away. So we're seeing them, 8, 9, 10, 11, 12, 13 billion years ago. And some of the blobs looked especially well-formed and bright and mature, even at an age of 500 or 700 million years after the Big Bang. And galaxy formation and evolution theories did not suggest that galaxies should form and become so mature looking so quickly. So this was an interesting puzzle. Now, it led to some viral headlines that were fake news. Big Bang didn't happen. Some people were arguing that because we found these mature-looking galaxies, the beginning of the universe 13.8 billion years ago didn't really happen, blah, blah, blah. The idea of a hot, dense, expanding universe, for whatever reason, we don't know the reason, but hot, dense, and expanding, that's the basic idea behind the Big Bang. That's on very solid ground. The early formation of galaxies, that's a puzzle we're going to have to figure out, okay? But this was complete baloney, and in fact, good science writers quickly wrote rebuttal articles. Here's August 22nd, just a month later. No, James Webb Space Telescope images do not debunk the Big Bang. JWST provides an intriguing look at the early universe, but it's not yet rewriting fundamental theories. Well, that was just a month after the first images were released. But by now, a couple of years have gone by, and it really is rewriting some of the textbooks. But it has not, led to a debunking of the Big Bang. Okay. Here's, this guy knows what he's talking about. Ask Ethan. He writes a very good article. Has the JWST disproven the Big Bang? No. No. Just ... no. Can't be much more emphatic than that, okay? JWST has truly blown our scientific minds, but it's a pure crackpot idea that the Big Bang is now disproven. Again, the idea of a hot, compressed, expanding universe at some time that we're still arguing about in the past 13.8, my team's data suggests 12.9 billion years ago, but whatever, those are details. Hot, dense, and expanding, okay? That's on very solid ground. However, we now need to understand, how did galaxies form and evolve so quickly? That's the wonderful aspect of science, is that if it's working well, it'll confirm some of the things you thought you knew, but it'll throw you interesting new tidbits and things, and new things to think about, okay? So there are two major explanations that have emerged for the existence of these luminous early galaxies. We think it's not so much a multitude of low-mass stars like our sun, but rather a relatively small number of exceptionally massive stars that emit way more power. I mean, it turns out that a star 10 times more massive than the sun emits 10,000 times more energy per second. And if it's 20 or 30 times the mass of the sun, it emits even more. So it's much more than a proportional relationship. And so you can have relatively few massive stars, and this is an artist's conception, emitting a lot of light, and if you attributed that light to regular low-mass stars like the sun, you would incorrectly conclude that there's just this multitude of stars. But there are relatively few very massive, very luminous stars. So that's what's making up some of these galaxies, we think. And then some of them, especially the ones that go by the name of little red dots, and they've been in the news in the past few weeks, in fact, and this is a brand new thing that's been published. What are the little red dots? Well, we think they're related to the following aspect that we've known about for the better part of a century. There are normal galaxies where the stars are more heavily concentrated near the center, because that's where gravity pulls them. But then there are active galaxies whose central regions are anomalously bright by a large amount. And they look just like a star. In fact, for a while, people thought this was just a star in our Milky Way galaxy that happened to be superposed along the line of sight. But there are ways we can tell that these are active galaxies, and there's something going on in the center that's producing a lot of light. What it is, we think, is a supermassive black hole. And indeed, Andrea Ghez of UCLA won the Nobel Prize a few years ago for work that she did using the Keck telescopes in Hawaii on Mauna Kea, showing that there's definitively a black hole in the middle of our Milky Way. But lots of galaxies have these so-called supermassive black holes, and they accrete, they swallow material coming in. And before that material crosses the boundary, the event horizon of the black hole, it can shine very brightly, and indeed, it's a very efficient way to shine. Once it's in the black hole, it no longer shines. But outside of a black hole, this is an extremely efficient process. And so what we think is going on is that supermassive black holes formed very early in the history of the universe, and that's a bit of a puzzle. And these luminous galaxies are these active galaxies, that is, giant black holes swallowing material. But now we have to figure out how these giant black holes formed so quickly. So we're not done. That's part of the fun of science, of course. The other thing you see here is a bunch of streaks like this. This, too, is a phenomenon that's known, but has been studied now more with the Webb. It's what's called gravitational lensing. So suppose we have a distant galaxy. Here's what the light would look like coming straight to us. But if there's a cluster of galaxies in between it and Earth, the gravity of that cluster bends that light, and it deforms the light from the background galaxies into these arcs, okay? And it brightens them. So it's like nature's telescope. It's like a gigantic magnifying glass or a microscope. I was talking with Gary there about microscopes over dinner, and it magnifies the amount of light, and in fact it stretches out the galaxies, in a sense magnifying them, but also distorting their shape. So this is not exactly like a microscope, but it's like a cosmic telescope, allowing us to see more distant objects that could be too faint even for the Webb, but once being magnified like this, though they're distorted, you can at least study the stars that are forming and stuff. And this gravitational lensing, the amount that we see, verifies that there's probably about 6 times as much dark matter, as we call it, as there is visible matter, because the visible matter associated with the stars wouldn't bend the light this much. You need 6 times as much gravity, yet we don't see starlight there. And so we think it's dark material gravitationally bending this light. Actually, it warps the shape of space, according to Einstein, and that then is what bends the trajectory of the light. But anyway, this too is not new, but is something that the Webb has verified. The new thing is the early formation of at least some galaxies and the fact that they have these supermassive black holes, blah, blah, blah. That's brand new, okay? So that's really cool. But anyway, I'm part of a team that has studied this gravitational lensing phenomenon, and in particular, if you take these little strips here, these distant galaxies, and you pass the light through a prism and you produce a rainbow, you get not only the colors of the rainbow, but these dark bands here, which are signatures of various chemical elements in the stars. And each galaxy has its own particular fingerprint, so to speak. So if you study distant galaxies, you can tell whether they might be images of the same galaxy. And the team that I'm on has some theorists who did a model of all the dark matter and all that, and they said that G1, G2, and G3 are actually 3 separate images of the same galaxy in the background of this cluster of galaxies. And we took a spectrum, so I'll be showing you brightness as brightness on the vertical axis as a function of color or wavelength. And that's what we have here, brightness versus wavelength, okay? And you get all these things here. And a trained spectroscopist recognizes this as being a couple of emission lines, we call them, caused by doubly ionized oxygen, and that bump is because of hydrogen, and that bump is because of hydrogen, and blah, blah, blah. Anyway, these 3 little dots have exactly the same spectrum, and so they really are the same galaxy. And this gravitational lens has magnified the light from that galaxy, and we're easily seeing it, even though this is a galaxy from when the universe was only 500 million years old. And when we published this study 2 years ago, this was one of the most distant or earliest galaxies known. I actually think there's one now, I should update the slide, that comes from when the universe was only 300 million years old. So that was done by a different team. So we're pushing things back, further back in time, trying to find the first generations of stars. But this was one of the most ancient galaxies at a redshift, so to speak, of 13. For those who maybe know a lot of astronomy, that tells you how much the light has been stretched during the expansion of the universe. So that's kind of fun. Let's switch now to more nearby galaxies. Here's something called Stephan's Quintet. There are 5 galaxies. It should be called Stephan's Quartet because these 4 are at about the same distance, 290 million light years. And this is an interloper that just happens to be along the line of sight. And here's a couple of yucky stars right there and there. Anyway, these are interacting with one another. And there's lots to say about this image, but they're colliding. These 2 are colliding with that one. And the compressed gas leads to enhanced star formation, which is kind of cool. And then eventually this one will collide. And then they look like a train wreck for a while, but then we think, according to computer simulations and images of other groups that are at a more advanced stage of their merging process, but we think they merge to form a single galaxy. And so we're seeing the future of the Andromeda galaxy and the Milky Way because they're actually approaching one another. Andromeda is so close to us that it's gravitationally bound to us. It's not moving away because of the expansion of the universe. We're in the same cluster. It's called the local group, and we're going to merge, and that process will start in about 3 billion years, and the thing will look like a train wreck for a while, and then computer simulations suggest that it'll transform itself eventually into a very different shape, something we call an elliptical galaxy, a little bit like this companion of Andromeda. There's another companion right there. And we even already have a name for it, even though this is billions of years in the future. Milk Almond Andromeda or Milkdromeda, depending on your preference, okay? So that's when Milky Way and Andromeda merge together. But we're seeing snapshots of this process when we study other such systems at various stages of merging. Okay, let's go to another form of science that's done. We can see through clouds of gas and especially dust, fine particulate matter, more easily at infrared wavelengths than at optical or ultraviolet wavelengths. It's even easier in the radio, okay? And so, you know, if it's a foggy day and you're in, I don't know, Honolulu or something, and you can't see an apartment building or an office building just a few blocks away, but you can still hear your favorite radio station, right? Because radio waves go through fog quite easily. Well, the infrared does that pretty easily, not as easily as radio, but we get better resolution, better clarity in the infrared. So we can see through clouds of gas and dust. So here's one of the iconic Hubble pictures, the pillars of creation, M16, Messier 16, the Eagle Nebula. We're now well within our galaxy, 6,500 light years away. And it was speculated that these are, you know, dense regions of gas and dust in which new stars are forming and have recently formed. But we can't see them because of the light being blocked by all the fine little particles. It's like the VOG or whatever. The sunset yesterday was pretty red. Did anyone notice that? Because the VOG from Kilauea, which is erupting again? Yeah. So you know, the violets and blues and greens all got filtered out, and the red is what got to you. Infrared gets to you even more easily through that junk. So this is a stellar nursery, pillars of creation. And here it is with the JWST. And let's look at a few regions. Let's look at this quartet of stars there. There's just no hint of it. I mean, well, maybe that's one of them. I'm not sure. But, you know, and then here's a bunch of stars, and maybe that's one of them. Here's a bunch there. I don't see them. Yeah. Anyway, and you can see the stars throughout. There's a whole bunch of stars in here that are that were newly born and were hidden by all the dust. So we're seeing stellar birth here. These really are the pillars of creation. Pretty amazing. We can witness stellar birth. And then you can ask, well, where did these dust particles form? How come the universe has so many of them? And there we study stellar death. And this is sort of a prelude to what our sun will look like, not in detail, but broadly speaking, in about 7 billion years. It'll first become a red giant, and then the outer atmosphere will become unstable, and there will be some gentle eruptions that'll kind of gently eject the outer atmosphere. Not a supernova explosion, but a gentle ejection. And then the remaining hot star illuminates the ejected gas and causes it to glow. Well, the Hubble pictures showed that star, but studies of it did not suggest that it was a dying star. It wasn't consistent. But here's a Webb picture, and it reveals another star whose properties do look what we think dying stars should look like. And what's going on here is that the ejected gases have started forming dust, and that dust blocks the ultraviolet and optical light. But the dust glows, and you can see also the star light itself coming through the dust in the infrared. So that's the dying star, and dust forms in typical dying stars like this. But not all dust necessarily forms in normal dying stars. Some might form in supernova explosions. So here's supernova 1987A. Gosh, time flies. I mean, I remember this object galvanized the field of the study of exploding stars into just a cottage industry. Here we are nearly 40 years later, my goodness. So that was an amazing event, and I'm part of a team that's studying exploding stars that were discovered 20 or 30 years ago. This one was 21 years ago. And now we're looking at them with the Webb, and we see that they are glowing more than they would be expected to if dust weren't present. So they're glowing because there is dust reprocessing whatever optical and ultraviolet light is still being emitted by the gases inside this exploding star. And if you plot a spectrum, again, brightness versus wavelength at infrared wavelengths, we have these data points. These are hard measurements to make, so we only have 9 or 10 data points, but not only are they clearly glowing, right, but we can fit a graphite model, basically carbon, pencil lead or charcoal, and that fits the data better than sand, a silicate model, right, silicon dioxide or whatever, which has this characteristic dip at 14 micrometers, which graphite does not. So at least this supernova produced carbon-rich dust, which is interesting. But here's another one that we studied that we just published this past year. That was supernova 2004 ET. They're named in order of discovery, but A, B, C, D, E, F, G, H, I, J, K. That's the 11th supernova discovered in 1980. Not of great interest to anyone, but in case you were wondering what the K stands for, that's what it stands for. And here you can see the brightness versus wavelength, and there is evidence of this dip. Unfortunately, we don't have a data point right there, but there's clearly not a bump there the way there was in the previous spectrum. It's more consistent with a dip. So it looks like this supernova formed dust that's more dominated by silicates, basically, So that's really interesting. So we're seeing different places from which dust originates, and that dust in the clouds of gas gravitationally collapses along with the gas and it forms stars, but debris disks around the stars coagulate into planets. And so, right, to have made Earth and the Moon, you needed a lot of this dust that would coagulate into planetesimals, and then they hit each other and form bigger and bigger things until finally you call it a planet. So, Earth's and we are made of star stuff, but that star stuff had to make dust particles somehow. So we're learning about that. Okay, another reason to look in the infrared is you can see colder objects. You might say, wait, didn't I show you though coals emit in the infrared, or aren't coals hot? Well, they're hot by human standards, but coals are actually pretty cool by astrophysical standards. And so, you can study cooler stars more easily if you go to the infrared, because the sun emits visible light and some infrared, and the totality of it makes what we call white light. And hotter stars emit ultraviolet, but cooler stars emit predominantly in the infrared. And here's sort of an exaggerated view of this. Again, the sun is not a yellow star, despite what you might think when it's setting, but that's preferential scattering and absorption by the atmosphere. The spectrum forms what we call white light. But anyway, 6,000 kelvins, roughly Celsius, slight difference. Visible light. A hotter star, 3 times hotter, emits primarily at ultraviolet wavelengths. And a cooler star, half as hot roughly, is in infrared, and this isn't even all that cool. There are some stars that go down to 1,000 or even 500 Kelvin, and this peak shifts way over into the infrared, okay? So it's a way to study very cool stars. And it turns out that at the star-planet boundary, there are these things called brown dwarfs. They're not quite a star in that they're not fusing normal hydrogen into helium. They're fusing a heavy form of hydrogen known as, the atoms are deuterium, but the nuclei are deuterons. They're fusing deuterons. By the way, the study of deuterons is known as Deuteronomy. You might not have known that, but that's what Deuteronomy is. Okay, at least that's one definition of Deuteronomy. I'm not saying that's the only definition of Deuteronomy. So these things, these brown dwarfs, they fuse deuterons for a while, but deuterons are only roughly a part per 100,000 compared to normal protons, normal hydrogen. So they're fusers, but they don't do it in the normal way for very long. And then there's planets that don't fuse at all, not even deuterons, okay? Great. So brown dwarfs are heavier than planets, but not quite full-fledged stars. They're at this planet-star boundary. They're interesting to study. And here recently are some images taken with the Webb. This roughly tells you the wavelength, 0.9 micrometers. That's almost optical. Your eye can't quite see that, but almost. And there's just like noise. And then 1.15 micrometers. There's something that looks like it might be real. 1.5 micrometers. It's there, I think. 2 micrometers. Yep. 3.56. Oh, wow. Now there's no doubt. And at 4.44 micrometers or microns, it's clearly there. So here's an object whose spectrum peaks way off in the infrared, you know, and this is a new, cold, distant brown dwarf. So that's kind of neat. And then even closer to home, I've been kind of, you know, going outward in, you can study planets of our solar system. And again, this is a color palette representing infrared light, but there's the great red spot. It doesn't look red there. And then the polar caps are a different temperature than the equatorial regions, and so that's why they look that color. But my colleague, Imke de Potter, she had a quote here, which probably NASA wasn't very happy with, but too bad. "We hadn't really expected it to be this good, to be honest," said planetary astronomer Imke de Potter, professor emerita at UC Berkeley, in a news release. This is just a month after the Webb, first results. And, well, NASA had better be glad that the reporter didn't quote me, where I would have said, frankly, I didn't think the darn thing would work at all, okay, you know, right? If I'm being honest, right? If I'm being totally honest, right? But I'm wrong, and that's great. But anyway, you can study planets, and of course, studying storms and stuff on the gas liquid giants tells us something about climate on Earth. Doesn't tell us everything because, you know, we have continents and mountains and oceans and all that kind of stuff. And so in many ways, these gas liquid giants are simpler planets. Nevertheless, studying long-lived storms like this one and what these little guys do when they go around and stuff, it can teach us something about climate on Earth. And then if you look at something like Neptune, this is a ground-based image with its bright moon Triton. Here was a Voyager spacecraft image in 1989. After it had passed, you can see overexposed Neptune there. It looks like a crescent. I think you can see it. Here's the glare. But then here are these rings, and we knew they were there because they tend to decrease the brightness of stars that happen to go behind them. But we had never actually seen them, and you can see the concentration varies as a function of where you are on the ring. But this backlit view where these things you're seeing because they're forward scattering the sunlight, that turns out to be a very efficient process. You can see faint things more easily when you're looking at the forward scattered light than, say, back scattered light or perpendicular. So 1989 was the last time we saw those rings because we'd not had a spacecraft out there near Neptune. And then here they are in JWST, and there's Triton, and you're supposed to say, yuck, right? But even though that's a moon. So let's get that out of the way. Let's zoom in. You see a little bit of the diffraction spike from Triton. But anyway, there's Neptune in all its glory, 6 of its many moons, the rings. And then you can watch, again, the development of storms and stuff. And so that can be useful. Okay, and then in my final topic, in the last just 4 or 5 minutes here, I'm right on schedule because I want to leave time for questions. Infrared spectra can reveal the presence of water and possible biosignatures and technosignatures. And that's really cool, you know. So first you have to find exoplanets that you can study. And the ones that we can study with the Webb are those that happen to have an orbit that's edge on to our line of sight. Because those are the exoplanets that once per orbital period transit across the face of the star. Some of you, if you were here in 2012 in Hawaii, how many of you saw the transit of Venus in 2012? Yeah, I was out here. I was in the Big Island. That's the last time for a century plus, folks. So if you missed it in 2012, looking at the ages of people here, unless Ray Kurzweil's nanobots save us all, or our AI, we download our brains and then we upload them to something else, we're not going to see that again. But exoplanets do this kind of thing, and the opaque part of the planet, which is most of it, blocks the starlight. Not much of the starlight, because the planet is generally small compared to the star. So this is highly deceptive. It says 98, 99, 100 here. So 0 is way down beneath the floor. The starlight dipped by only 1.5%. But that's enough to notice. And indeed, there are now amateur-sized telescopes like these unistellar EV scopes and equinoxes where hundreds of astronomers looking at the same star the same night can gather up all their data and detect these exoplanet transits. So that's great. These are the ones we like. Then what do we do with them? Well, you see this gray area here. That's a putative atmosphere. And so starlight that passes through that gray area to our telescopes, in particular the Webb, could be absorbed at certain wavelengths, depending on which atoms and molecules are in that atmosphere. So this, again, is not anything new. It's been done before. You make a spectrum like this, and indeed, this star here was studied ages ago with the Hubble Space Telescope. They took a spectrum of the star during a transit and compared it with a spectrum of a star, of the same star, not during a transit. And of course, the star is fainter during this transit by a tiny bit, but who cares? These two lines, which are characteristic of neutral sodium, were stronger relative to other absorption lines during the transit than not during the transit. So that means there's sodium in the atmosphere of that exoplanet, because the spectrum only differed during the transit from not during the transit by this greater relative strength of the sodium lines. So they were produced by sodium atoms absorbing certain wavelengths of light in the yellow-orange part of the spectrum. So that's great, okay? So this has been done, but now it's being done with the Webb. And in the infrared, there's the chance of detecting some really interesting things. Here again is brightness versus wavelength, and there are a bunch of noisy data points here. These are very difficult measurements to make, even with something as powerful as the Webb. But you can see here this faint blue line is a model that is fitted through the data points, and the bumps and wiggles are basically formed by water molecules. So water has been detected in the atmosphere of this exoplanet, WASP 96b. B is the exoplanet, 1,150 light years away. And it's doubly interesting because this is what's called a hot Jupiter. It goes around the star with an orbital period of something like 3 days, 3 plus or minus 1, doesn't really matter. It's really close in, right? Mercury, the closest planet to Earth, orbits in 88 days. So imagine a planet orbiting in 3 days. So it's being blasted by radiation from that star, and yet water is able to survive in the atmosphere. So that bodes well for the presence of water in atmospheres or in ice form for the colder ones, but on many exoplanets. And astrobiologists, right, those who want to study biology elsewhere, it's a data-starved subject so far, but maybe not forever, right? You can study it to some degree by looking at living organisms in extreme environments, extremophiles, like in Antarctica or deep underground or in, sulfurous geysers or whatever. But anyway, their mantra is follow the water, because at least on Earth, the water we know of, the life that we know of is always based on water, right? Water is this wonderful molecule. It's very polar. It dissolves things, salts and stuff, and then they can form compounds, and then who knows how life formed, but we think somehow life formed. And if it's anything like that elsewhere, Maybe it's not a unique way of making life, but it's clearly a very good way of making life based on the number of species that are on Earth now. And maybe life, if it evolves enough, eventually replaces itself with silicon-based life, as we appear to be on our way of doing. I don't know if you're thrilled by that or mortified by that, but I don't know. A century from now, I'm not sure humans will be relevant anymore. I hope we will be, but I don't know, folks. I'm not some Luddite who thinks AI is, just don't use it. I mean, you look at AlphaFold or something where they can, in minutes now, figure out how proteins fold and try to figure out, various ways to prevent or cure diseases and stuff. So amazing, things that could be done, but I'm also a bit worried about what might happen to Homo sapiens. And so, but in any case, maybe throughout the Milky Way, silicon-based life dominates, but we think, at least I think, that it originates carbon-based and water-based. So if you find a spectrum like this, other people will start using their telescopes to start studying that exoplanet. Even more so if you were to detect technosignatures, or at the very least, additional biosignatures. And so here's a synthetic spectrum. This is not an actual one based on data. But if you were to find oxygen, here in the case of ozone, with methane, CH4, that would be really interesting because methane oxidizes very quickly in the presence of oxygen. And so to have methane and oxygen simultaneously means that there has to be some reasonably continuous source for the methane. And although there are just chemical abiological ways, that is non-biological, to form methane, we see varying amounts of methane in Mars's atmosphere, and most planetary astrophysicists and astrobiologists don't think that that's very significant sign for life. They think it's just produced by chemical reactions. So it can be produced by chemical reactions, but it's also produced by the decay of living organisms, right? Carl Sagan eloquently called it bovine flatulence, right? So there you go, methane, right, bovine flatulence. So if we were to see that, that would be highly interesting. Not definitive evidence for life, but highly suggestive. Plus there's some water here. And then if we found some pollutants, for example, chlorofluorocarbons, which fortunately either aren't used much in refrigerators anymore, or they trap them better than before, or maybe a combination of both. But those, the CFCs, remember, are what destroys the ozone layer, and scientists realized that decades ago, and the ozone layer has largely recovered, right? Because we don't let all these CFCs out anymore. But if we were to find a pollutant like that, that's not so easily formed by nature, that is not, intelligent in some way. I mean, I'm not saying we're not part of nature, but by a non-intelligent, just regular old chemical reaction, doesn't tend to form CFCs and other types of pollutants that we have made. So if we found something like that, that would be really interesting, and everyone and their grandmother would start pointing their telescopes toward it. So we'll see. This is, I think, a long shot with the James Webb, but it's not completely out of the question. But anyway, because the engineers aimed the thing so well at the L2 point, they had to use very little of their fuel to give it some little kicks into the L2 point. So they didn't have to cheat much. It's like, you're playing golf, and instead of remaining on Maui here, you want to aim towards San Francisco or New York, and well, there's not many places between Hawaii and San Francisco, so you can't cheat very easily. But suppose you're playing golf in San Francisco and you're aiming for New York, and people cheat in Kansas City and Chicago, and they alter your ball's trajectory a little bit, and then you hit a hole in one. Well, that's not such an accomplishment, but if you went all the way to Boston and then cheated a little bit, that's pretty good, okay? So they didn't have to cheat very much with JWST, and that means there's a lot of propellant left to nudge the thing back into place after it gradually starts wandering away from the L2 point. And so that means that its anticipated lifetime is 20 plus years, not just the nominal 4 or 5, at which point NASA would have declared victory. And it's primarily because they didn't have to use much fuel to nudge it into the L2 point. So unless some some asteroid hits it or something. It's not in the area of low Earth orbits. So there's not much space junk there. There are a few other things at L2, but mostly we have to worry about rocks hitting it. So if a rock doesn't hit it, maybe 20 years of useful results. So stay tuned. And we, of course, couldn't do any of this kind of work without the generous support of not only the US government, but now progressively more individuals, families, foundations, companies. And I just saw a headline today that, science may or may not, we'll see, be in trouble. But yeah, so can't do this kind of work without your support and your support of the concept of observatories here on the ground. So anyway, I'll take questions and hopefully be able to answer a whole bunch of them. So thank you very much for your attention. And I'll be happy to repeat the questions for the benefit of everyone. And this is apparently being taped and also on Zoom as well. So yes, go ahead.
So is dark matter considered to be transparent at all relevant frequencies?
Yeah, so is dark matter considered to be transparent at all relevant frequencies? Basically, yes. It doesn't interact electromagnetically, like with light, basically. And so it doesn't emit any light. It does respond to gravity, so it congregates where the clusters of galaxies are and where the galaxies are. It also, we think, interacts via what's called the weak nuclear force. So one of the top ideas for what the dark matter is WIMPs, weakly interacting massive particles. But my laboratory physicist friends have been searching for WIMPs for over 40 years now and still haven't found them. Now they're hard to find because they hardly ever interact, but with enough years and sensitive enough lab equipment, occasionally one of the many WIMPs that's going through us all the time, so we think, would interact with the detectors, and so my physicist buddies should detect them, but so far not yet. I'm not yet totally worried, but at some point, if they don't find them, I'll be pretty concerned that that's just not the right solution. Another type of elementary particle is known as an axion. It's even harder to find, but it's predicted from other aspects of the so-called standard model of particle physics, and those haven't been detected either. If it's not WIMPs and axions, I'm not sure what it is. Maybe it's completely wrong. And so it could be that dark matter, which helps bind galaxies and clusters of galaxies together, and dark energy, which I didn't talk about today, but it's the stuff that seems to be accelerating the current expansion of the universe. That's what I talked about 15 years ago here. We don't know what that is either. Those could be what I like to call our 21st century Ptolemaic epicycles. Ptolemy had this Earth-centered theory where everything goes around Earth and the planets go around Earth and the sun goes around Earth. But he needed little epicycles, little circles on top of circles, so as to explain the apparent backward movement of planets among the stars every year. And you could add additional epicycles, even though he did not. The data weren't good enough to, necessitate that. But it was a brilliant mathematical technique. In fact, it's the basis of what we now call Fourier analysis after Fourier many hundreds of years later. And that could have been as accurate as you want if you add more and more epicycles. But it was fundamentally wrong. Not to say that Ptolemy wasn't a smart guy. He didn't have the data to show that it was fundamentally wrong. And it was enormously successful for predicting where planets would be. 1,500 years of success, okay? But wrong, as we saw after Galileo started making observations. So are dark matter and dark energy just our current best explanation for these weird things that we observe in the universe, but they're fundamentally totally wrong? I wake up in the middle of the night, 3 o'clock in the morning. My wife, who has heard me give this talk before, so she opted not to come. She's just chilling, Maui style, She could vouch that I could wake up sometimes in the middle of the night worried about how dark matter and dark energy are just completely wrong. But I don't know what we'll do about that.
The cartoon?
Well,
He's thinking about other women. Except what he's really thinking about is dark matter.
Well, there you go. That's right. There are various variations of that joke, right? Yeah, that's right. There's one in France where one physicist is talking to another, and I hope no one gets offended by this. They're saying, is it better to have a mistress or a wife? And one says, well, a wife, of course, long-term stability and all that. And another one says, well, no, a mistress, And then the third one says, no, it's best to have both, because when the wife thinks you're with the mistress and the mistress thinks you're with the wife, you can be in your lab doing your experiments. Okay, so, okay, how about another astrophysics question? Yes, go ahead.
So what really piques my interest is exoplanets, and particularly like the TRAPPIST system, which possibly has 4 planets in the Goldilocks zone. And I think your last talk up at Fukuoka, I was there. And
oh, thank you.
Telescopes that were under construction and would be coming online. And forgive me if I'm hallucinating this or wishful thinking, but I think you talked about a telescope that was going to be online that can be trained toward a star system, block the light out of the sun.
Yeah.
So that we can, or the stars, so that
that's
we can
right.
see the planets.
Yeah, I think that'll be, for those who didn't hear the question, or maybe those online, exoplanets, and the last time I gave a talk here, I mentioned them, and that there is in the plans a telescope to essentially block the starlight to see the planet. I think, but I'm not sure, that that's the basis of the design of what's called the Habitable Worlds Observatory. You can look it up online. NASA has plans already. It's still easily a decade or two in the future, probably 20 years. I'm not exactly sure of that either. But I think they will have one of these blocking devices. Yeah, that'll be pretty interesting, because then you could image the planets more easily and isolate them to get a spectrum and all that, yeah. And there are various more or less clever ways of doing that, because if you just block the starlight with a disk, then you get this diffraction pattern, right? This stuff that I was talking about, these yucky things right there, right? But there are ways of decreasing the effect of those things. And I've seen, and I'm not an exoplanet astronomer, so this is not an area that I've spent a lot of time thinking about or reading about, but I've seen various designs that look almost like a sunflower for the blocking element, and that somehow decreases the magnitude or the severity of this diffraction pattern. So yeah, there are more and less clever ways of making the occulting disk. SOHO, for the Solar and Heliospheric Observatory, uses just the simplest thing, a disk. But it's 2 or 3 times the size of the sun's apparent disk, okay? So it's still useful to study the corona during a total solar eclipse, because you can see the inner corona and the chromosphere, whereas with SOHO, you only see the mid and outer corona. But they want to find coronal mass ejections and find out, when big bundles of charged particles are coming toward Earth, warn the power companies and all that. But one reason they did such a big disk is if their disk had been just the apparent angular size of the sun's disk light is so bright that the diffraction pattern would have just destroyed their, well, maybe it wouldn't have destroyed the detector, but would have seriously compromised the data quality for the corona and other things they're trying to find. I saw, there was a question, right? Well, okay, I'll go back there first, and then, yes, go ahead.
What do you personally think is the probability of finding, water-based life out there somewhere?
Yeah, the probability of us finding it versus the probability of it being there are very different questions, okay? Yeah, 2 different questions. So that's a long thing. I'll try to be short just to do a bunch of questions. I see a few more hands up and stuff. But so this is just an opinion, okay? And we need to keep exploring. But my opinion is that primitive, by that I mean microbial or bacterial life, may be reasonably common, although I'm not even absolutely sure about that. But it did form within the first 100 or 200 million years on Earth, after the era of late heavy bombardment about 4 billion years ago. We can tell that that happened because that's how old most of the lunar craters are and stuff, you know. So it ended, 4 billion years ago, and there's chemical evidence for life 3.8 billion years ago. Okay, so that's pretty quick, 100 or 200 million years. So if that's typical, then primitive life may have formed very early elsewhere as well. But who knows, maybe we were an outlier in how quickly it formed here. So that's not even necessarily secure conclusion. But then if you go from life nearly 4 billion years ago to us, whoa, Homo sapiens, 250,000 years ago, 250,000. Early hominids, 4 million years ago, out of the 4 billion year history of life on Earth. That suggests to me that we are a very rare and very low probability evolutionary outcome, all right, that may occur only very rarely, especially if we are on the short side of formation here on Earth, right? I mean, what if it typically takes 12 billion years to get from the bacteria to us, right? We don't even know where we are in that distribution. And if it's rare, and by the way, the other aspect that tells you that it's rare, not only did it take a long time to get to Homo sapiens, but there have been several hundred billion, there are arguments, how many 100 billion species of life on Earth in the history of life on Earth. Nothing has come close to us through a different lineage than the great apes and all that, right? Dolphins and whales are pretty smart. I was just listening to dolphins this morning while snorkeling. It's wonderful, actually, yeah. But, there's no evidence they think abstract thoughts. They don't have an opposable thumb with which to build particle accelerators and telescopes and things like that. So, they're intelligent, but they're not Homo sapiens, okay? And there's nothing else in the fossil or DNA record that indicates a different lineage that almost forms something as intelligent as us. And then there's the Fermi paradox. The next argument is that given what we've done, maybe we're just beginning billions of years of a flourishing existence, or maybe we're near the end, either intentionally or unintentionally or through neglect, right? We are 1 century into having the capability of destroying ourselves. What are the odds we're at the beginning of 1 billion years of a flourishing future? I don't know. So maybe, maybe this is a nearly ubiquitous aspect of intelligent, quote unquote, life and life that's able to build machines and stuff, is that it has these self-destructive powers. So they're like flashbulbs in the night. So I think they're rare, and I think we are flashbulbs in the night. And then that helps explain the Fermi paradox. If they were common out there, why haven't we seen more obvious, definitive evidence of them? Why aren't we the aliens, basically, right? It's like ants. They're all over the place, right? If there's only a few in our galaxy, yeah, maybe none of them is sufficiently ahead of us or decided to not populate the galaxy. But if there are scads of them, as Carl Sagan thought, he thought there might be 100,000 in our Milky Way galaxy. Odds are a bunch of them are way ahead of us. Odds are they've conquered interstellar travel with computer chips and stuff, not flesh and blood. And once you conquer interstellar travel, it's actually quite fast to be able to populate a galaxy, because it's like you send out a thing, it doubles, and then doubles. It's exponential growth. It's COVID-19, So it doesn't take long to populate a galaxy if even one civilization wants to do that. And they're not here on Earth. And we've heard silence out there. And again, we've only been searching for a while, but the silence is deafening. So all those arguments, to me, suggest that intelligence at our level is extraordinarily rare. I don't think we're alone, certainly not in the observable universe, these trillion galaxies that I mentioned. But we might be alone in our Milky Way. That's not a completely outrageous or self-centered perspective. It may sound arrogant and stuff, but it's not actually. But I'm all for continuing to search, because if you don't search, you almost certainly won't find. And then in terms of primitive life that's water-based out there, you know, some of my colleagues think, oh, it's in the solar system as well, elsewhere. Indigenous, I doubt it. Because if it's indigenous on even another moon or planet in our solar system, then it means it's everywhere, and it's super easy to form life. And I personally think that life formed as a result of random molecular combinations that eventually just by chance made something that self-replicated and evolved and all that. And I don't know, I personally think that's pretty darn rare. And of course, this is where, you know, one's religious beliefs and spiritual beliefs and all that can play a role. And the answer is we don't know. And even with science, we don't know ultimately what the purpose or origin of life is. We can just ask from a purely biological and chemical reaction process, can it occur easily or not so easily? And I fall on the not so easily part of the spectrum. But obviously all bets are off if there's some greater being out there that says, look at all these exoplanets, which I created, let there be life on all of them, right? And that's possible too. But I don't see evidence for it, at least not intelligent life, okay? So that's my view, but it's just an opinion, okay? So, yeah, I think JD had, or no, there's a question right there. Yeah, Paul, right.
A question about the gravitational lensing.
Yeah, the gravitational lensing, yeah.
Is it possible to deconvolve those distorted images and come up with anything at all?
Yeah, can we deconvolve the distorted galaxy images with gravitationally lensed objects? If we have a good enough model of the lens, but often it goes the other way. They say, okay, that looks from its spectrum like a spiral galaxy. Let's now figure out what it took to distort it into that arc, right? And so that then goes into the dark matter model, the distribution of dark matter. But you've got a lot of data points, and so, yeah.
I'm just wondering.
Yeah, not absolutely sure how reliable the deconvolved or the de-distorted images would be. Not sure. Let me ask one of my theorist friends, and email me that question, Paul, and I'll try to answer it with greater authority than I'm able to do right now. But I think that often like I said, it goes the other way. You sort of say, okay, from the spectrum, this had a whole bunch of young stars. It's probably a spiral galaxy. And to get it to be this distorted, that is input into the model that gives you the amount and distribution of dark matter. So whether it can go the other way, I'm not sure. I saw some, JD, yeah.
Yeah, we've got an online question.
Oh, an online question, okay, great.
So, is James Webb studying Kuiper belt and Oort cloud objects looking for Pluto II?
Yeah, so is the James Webb studying Kuiper belt objects and Oort cloud objects and Pluto #2, or Planet 9, as my former student, Mike Brown, he's the one who's most responsible for demoting Pluto. You may agree or not agree, but it's one of many Kuiper belt objects, and Eris and a few others are about the same size. And so what he did makes a lot of sense. But now, through studies of some of the Oort cloud comets, Sedna and some others, they're finding interesting distributions of comets that suggest a gravitational interaction with a genuine Planet 9, they call it, beyond Neptune, well beyond Neptune. They're not sure exactly where it is. And it hassles these comets and makes them take on these preferred orbital trajectories. That's the nature of the argument, okay? To find it, you have to scan giant parts of the sky. So no, the James Webb Space Telescope with its tiny detectors is not searching for Planet 9. Ground-based telescopes that scan big parts of the sky are searching for Planet 9. However, individual interesting Kuiper belt objects that are already known are being studied by JWST. You might want to get their infrared spectrum or something like that, but they were discovered through ground-based surveys where you take photographs night after night, and you see these little things zipping across the sky, well, not zipping is the wrong word, but just slowly moving among the so-called fixed stars. And that's how you find them. But you have to look over vast regions. And, you know, Mike Brown has this really good talk. You can probably find it online somewhere, The Search for Planet 9. And the talk is now 5 or 7 years old or 8 years old. Don't remember whether there was a version pre-pandemic. I think there was. And he said something like, within 5 years, we will find it. But no one has found it yet. Believe me, it'll be big news if and when it's found. Their arguments to me, and again, I'm not a planetary astronomer, but their arguments to me seem pretty convincing. But there could be other ways to force comets into these particular trajectories. And to be fair, the number of comets studied is still so small that it's not clear whether these so-called, quote, preferred orbital distributions are truly something out there in nature or a statistical anomaly, right? Maybe Mike would get mad if I were to say that maybe there's enough comets now, but at least in the early years, it wasn't clear to me, listening to their presentations, whether the 5 or 6 objects they had were a statistical anomaly or something real, you know. Probably they've now advanced the field to some degree. But no one has found Planet 9 yet, the genuine Planet 9. So there you go. Maybe it's not actually there. Yeah, good question online there. Good. Yes, go ahead. Or how about, since you just did one, let's go to Rob there.
Alex, what do you mean by obscuring dust? How big is it?
So how big are the particles of obscuring dust? They're just, they're roughly half a micron in size to a micron, and that's precisely why they block visible light, but not infrared. The infrared can bend around them, basically. And indeed, they block the visible light in a highly differential way. That is, the ultraviolet and violet is blocked more than than greens, which is blocked more than reds. And that tells you that they're roughly half a micron in size, okay? Yeah, it's a little bit like the stuff scattering and absorbing blues and violets in our atmosphere. I mean, there's several effects. There's what's called Rayleigh scattering, which is a pure scattering of light from nitrogen and oxygen molecules. And there, that's a function's proportional to frequency to the 4th power. So inverse wavelength to the 4th. So let's say you take blue light, roughly 400 nanometers, versus red light, a bit redder than red, but let's call it 800 nanometers. Okay, that's a factor of 2 in wavelength, factor of 2 in frequency the other way. Factor of 2 to the 4th, or 16 times more scattering, which is why the sky is blue. You might say, why isn't it violet? 2 reasons. The sun doesn't produce much violet light, and our eyes aren't very sensitive to violet. The sun produces lots of green, and our eyes are very sensitive to green. So why isn't the sky green? Because the scattering for green isn't as good as for blue. Blue is the happy medium between really good scattering and a fair amount of sunlight is blue, and our eyes are pretty good at detecting blue. So that's the happy medium. So that's Rayleigh scattering. Then there's the dust, and that's much closer to 1 over wavelength, or proportional to frequency. So nowhere near as great a dependence on the power of the frequency, not to the 4th power, but just to the single power. Nevertheless, 400 nanometer light, blue light, gets absorbed and scattered more than 800 nanometer or red light. Okay, so that's what produces the red sunset yesterday. There's a bunch of fog out there. And it's got a whole distribution of particle sizes, and physiologically, from what I understand, but I'm not an expert here, it's the PM 2.5s that are the worst for your lungs and stuff, the 2.5 micrometer particles. So those are the size of infrared photons, near infrared. But there's a whole distribution of the stuff that the volcano spits out. And what's causing the red sunsets is the roughly half a micron, 500 nanometers stuff. So yeah, these little dust particles form, and then they coagulate into bigger ones and stuff. But yeah. Then you had a question there.
Well, it was very related to
Yeah,
that.
oh, okay.
like if we were in the pillars of creation,
Yeah.
if Earth was, the sun was there in that particular period of
Yeah.
creation, what would, and we happen to be there, what would it be like? Would it be just like watching that foggy thing? Or would we be like totally...
Oh, well, yeah. So the question is, if we were in the pillars of creation, what would we see? Some foggy thing or what? We'd see some nearby stars very brightly because there's just not much stuff between us and them. And then the progressively more distant stars would have more dust between us and them, and more of their blue and violet light would get scattered out. But depending on where you are within that cloud, I mean, if you're smack in the center, then yeah, looking out in every direction, you'll see progressively more dimmed stars that are closer to the edge of that distribution of dust. But if you're close to the edge...
Inhaling it and going...
No, I see what you're saying. No, would you inhale it and go... Oh, no, these are all still very low densities compared with anything on Earth. We're talking about, okay, our atmosphere, I think... Is it 10 to the 19th molecules per cubic centimeter? Something like that. I think it's 10 to the 19th is the number I'm remembering. And a dense molecular cloud, which is a birthplace of stars, is 10 to the 6th, 1,000,000 particles per cubic centimeter. So these are like vacuum compared with what we produce. I mean, we can produce better vacuum on Earth, but this would be a really good vacuum. But compared to interstellar space, which is 1 particle per cubic centimeter, that's the average density of the so-called interstellar medium, the stuff between the stars in the typical place. Okay. Then the dense molecular clouds, a few hundred, tens of thousands, 1,000,000. Some of them might get up to 10 or 100 million particles per cubic centimeter. And then, of course, where a star is forming, it's getting denser and denser, obviously. But but that's still better than most vacuums here that we produce on Earth. So you wouldn't be choking on this stuff. Yeah. Yes. Mm-hmm.
Earlier, you showed the spectra for a protogalaxy, and I noticed that the O3 line was way stronger than helium and hydrogen.
Yeah.
Which was interesting.
Ooh.
How much helium and hydrogen there was in the galaxy. Could you tell us more about what these early galaxies looked like?
Oh my goodness.
Cosmologically and, like, kind of...
Let me repeat this because are you a student of astrophysics? No? Yeah, it's quite a sophisticated question. The gentleman's question is, in the spectrum that I showed, the oxygen emission lines were considerably stronger than hydrogen and helium emission lines, and yet hydrogen is by far the dominant element in the universe, and helium by far the second most dominant element. I mean, oxygen may be prevalent in our atmosphere, though it's only about 20%, by the way. Most of our atmosphere is nitrogen. So why are these oxygen lines so strong? Okay, great question. All right, it turns out that doubly ionized oxygen is a really good coolant. Now, what do I mean by that? It turns out that the doubly ionized oxygen collides with electrons, all right? And those electrons give some of their energy to the oxygen, and it makes an electron in the oxygen jump to a higher energy level. And then from there, it decays down to a lower energy level, and it emits light. But what you're doing is you're taking kinetic energy from the free electron, right? You're decreasing the kinetic energy, so you're cooling the gas, and you're radiating away the photons. So it's a better coolant than hydrogen or helium. And so you get strong emission lines. Yeah. That turns out to be quite a subtle effect. So there you go. Great question. Yeah, great question. Yeah, I have to tell you that in all my years of giving public lectures, that is the first time that question has come up in a public lecture. It's come up in class where we're studying the astrophysics of gases or whatever, but that's what the students are supposed to be thinking about. But that is, congratulations, the first time I have ever been asked that in a public lecture. So listen, I'll be putting away my stuff, but if you want to come up and chat or whatever, you're welcome to do so.